Starting recording now. Okay, recording has started.
Okay, I'm going to start the presentation now. Hello, everybody. I'm Bishr Asil. I'm your friend from Mechanical Engineering Department, so please excuse me if I get some of the technical jargon wrong. Today, I'm going to be speaking about relevance feedback and query expansion. So what is relevance feedback? There are many utilities that we can use to improve the results of our query, and one of those utilities is relevance feedback. By using relevance feedback, we identify the top documents found by query as relevant, and we identify some documents as non-relevant. These documents are then examined, so they may be deemed relevant or non-relevant either by manual intervention or by an assumption that the top documents are relevant. We will be speaking more in detail about this later, but this is just a basic definition for now. There are various techniques to rank the terms that are used in the documents. The top terms from these documents are then added back into the original query. We will raise the original query. Of course, not only adding back is the only way, but this is just a basic definition. We can just change the weights. We will be talking about this more later. So the result is that we want a new query that is closer and will give us better, more relevant documents when used again in a retrieval strategy. So the basic premise is that we implement a retrieval strategy in multiple passes, and the user will refine the query in each pass based on the results of the previous queries. Typically, the user indicates if these documents are relevant or not, and then new terms are added to the original query based on this selection. So to explain it, so hopefully everybody will understand, our user will give us a query that will go into a retrieval system. So for example, let's say this is a vector space model. And then out come some results. These results may have relevant documents, they may have non-relevant documents. So our user will take these results and then they will tell us if these results are relevant or not. So for the example, this example specifically, the first two documents are relevant and the third document is not relevant. We will take these results and then make a reformulated query based on them. So this new query, we'll put it again into the search system. We'll do another pass, and the outcome hopefully is better results that are more relevant for our users. This is a real example that's used for relevance feedback. PubMed is a popular medical website. In this search, you can see that, for example, they search the term MRSA, which I assume is some sort of disease. And their users are asked to give feedback about the relevance of these documents. Now, as you imagine, this is very tedious. You'd need to open the document, you need to look through it and read it, and then you would have to decide if it's relevant or non-relevant. And then you'd have to give feedback to get new documents. This is very time-consuming. So an alternative is that you can avoid using the asking the user anything at all and just assume that the top ranked documents are relevant. We will be talking about how to use this correctly later. Okay, so to recap, and hopefully everybody will understand, we will get an original query that has some amount of terms, QI. We will place it into a retrieval strategy, and then using relevance feedback, we will get the results from the original retrieval strategy. We will create a new, richer query. And with this richer query, we will place it back into the retrieval strategy again. And if needed, we can use relevance feedback again. And the amount of iterations will also be explained later. Okay, so when you're talking about relevance feedback, Rochio's algorithm is one of the more important things to understand. So Rochio's algorithm basically says, imagine we have a domain that has some non-relevant documents and some relevant documents. We know these are relevant, we know these are not relevant. Our initial query might be closer to some non-relevant documents than relevant documents. So what we're going to try to do is move our query to where the vector of it is closer to more relevant documents. And as you can see, our revised query is much closer to known relevant documents. That's the basic premise of Rochio's algorithm. How do we do that? Well, this equation, which looks a little complicated, I'll explain it now, basically says that our new query, our refined query, is a combination of our old query, the amount of the term that happened in a relevant document, and the amount of times the term has come in non-relevant documents. We will take our old, we will add the amount of times that this term came in our query and in relevant documents, and then we will subtract it from non-relevant documents. We have alpha, beta, and zeta, which are weights for each of these terms. We will be talking later about how we determine these weights. But for now, this basic equation, I'll be explaining it with an example. So let's say our original query is find information surrounding the various conspiracy theories about the assassination of John F. Kennedy. And just as a precursor so that we understand the example better, there's a person who I believe is named John Oswald who is involved in some of these conspiracy theories. Okay, so find information surrounding the various conspiracy theories about the assassination of John F. Kennedy. This query has some good terms that we would like to use and focus on. For example, the words assassination, John F. Kennedy, and conspiracy. But it also has bad terms that are not stop words, so we can't just take them out, such as information, various, or surrounding. But there's also the term Oswald. This is not found in our original query, but the term Oswald may be in a lot of high-ranking documents, so that we can expect if we added the term Oswald to the original query, that we will get much better precision and recall with much better relevant documents. So if a top-ranked document is deemed relevant by the user, has a lot of the term assassination, the weight of the word assassination for later queries should be increased. Please note that currently there's no accepted way of adding new terms to the initial query in the probabilistic model. Even though right now we're talking about the vector space model, this is generally the relevance feedback model, so I do need to make that note. We'll be talking later about the probabilistic model in more detail, but this is a very important thing to note. Okay. I think I lost the presentation. Yes, okay. So as I said before, the weights, alpha, beta, and zeta are referred to as Rochio weights. The values of these weights was experimentally obtained. So for your own example, you might need to obtain them on your own. But it is considered as very common today to just drop the use of non-relevant documents, or in other words, assign 0 to the zeta or the weight of non-relevant documents and only use the relevant documents. Okay, so let's give an example. Given that our initial query is cheap CDs, cheap DVDs, extremely cheap CDs, we returned 2 documents. The first one, cheap CDs, cheap software, cheap CDs, is judged as relevant, let's say by our user. The second document, cheap thrills DVDs, is judged as non-relevant. This example only contains 2 documents, so everything will be simpler. But of course, in the real world, everything is much more complicated. So what would our query vector be after using relevance feedback on this query? Now, please notice that we are assuming the weights that we will use. And as I said, these weights are usually obtained experimentally, but for our example, we'll just assume that these are the weights. Okay, so we have seen this table many times. We know how to make it. So this is the table for these queries and documents. Okay, so QM is our modified vector. How do we obtain QM? Well, let's do it with an example for the word cheap. How should cheap be in the new query? So cheap in the new query, as given by our equation, is a combination of the original query, it occurred 3 times there, plus 0.75 times the times it occurred in relevant document, so multiplied by 2 is 1.5, and minus 0.25 times the times it occurred in a non-relevant document, which is 1. Now, this is a very simple equation here, but if you look at it, this is just because, let's head back a little bit. We don't have, we only have one relevant document and one non-relevant document, so sigma is dropped and n is dropped because they're both 1. So that's why these are so simple. But if we have more documents, this will be much more complicated. Okay, so the new query vector for the word cheap is 4.25, which basically means that now we're adding more weight to the word cheap. We are basically telling the retrieval that the word cheap is very important in our query. We will get more relevant documents if we have more of the word cheap. So we do the same thing with all the other words. Some words will be, okay, this is worse. The word DVD gave us a non-relevant document. So it's not a great word to have, but we don't eliminate it completely. So for the word thrills, it occurred in only non-relevant documents, and we didn't even have it in our original query. So it should be negative, right? Well, no, negative weight doesn't really make sense to have in a word, because right now just using this search, maybe later you will use something else. So we don't want to penalize something for just being in the wrong place, if that makes sense. So we just make it 0. We leave them as 0 if we get a negative revised query. If you just excuse me for 1 second. Sorry, I just had to take a sip of water. Okay, continuing on. There's more details about this this equation that I talked about here and how we use it for the vector space model in the reference book. There's also different equations. For example, this is the Dekha equation, where basically we only look at the first or the top non-relevant document, and we ignore the amount. We also don't divide by how many documents it occurred in. This is also a different equation that can be used, but this all leads to a very interesting problem, which is that what if we only retrieve non-relevant documents? So an approach suggests that we should just add an arbitrary weight to the most frequently occurring concept in the document collection, not term, but concept. This can be generalized to increase the component with the highest weight. And we hope that this term that happened in the that occurred the most is important, but it was drowned out by all the surrounding noise. So by increasing its weight, the term now rings true and yields some relevant documents. But do note that this approach is applied only in manual relevance feedback. You can't have this in automatic feedback, as you can't have non-relevant documents in automatic feedback. For automatic feedback, we just assume that all the top documents are relevant. So you can't really have you can't really only retrieve non-relevant documents by definition. Okay. Also, I forgot to mention, if only non-relevant documents came, this could be a user error. So this is something to keep a lookout for as well. Okay, so now we're done with the vector space model. Let's look at the probabilistic model. Probabilistic model is well suited for relevance feedback because, as you remember, it's necessary to know how many relevant documents exist for a query to compute the term weights that we will use in the probabilistic model. So typically, the probabilistic model requires some training, data. But once the term weights are computed, they can be applied to another collection without the need of training. So probabilistic relevance feedback plugs into any existing retrieval strategy. because you're just adding more weights to the terms. So it's a very general relevance feedback strategy. So how do we get this training data for the probabilistic relevance feedback, probabilistic model, sorry. Our initial query is executed using an arbitrary retrieval strategy. For example, we can use vector space model as for our initial execution, and then we can incorporate the relevance feedback that we talked about earlier into the probabilistic model. So as you know, for this equation, to find the weight of a term in a particular query, we have two variables that we need to know the amount of times a term occurred in a relevant document. You can't have this unless you have training data, or now with relevance feedback, we actually can know how many times a term occurred in a relevant document, or we know how many relevant documents there are. So with that, we can compute the weights that we will use in the probabilistic retrieval model. So with that, we don't need training data. So as I said, this is basically what I just said. Some variables cannot be known unless we have training data, but with using a different retrieval strategy, we can observe the top few documents and assume that they're relevant, for example, and then use that in determining the weights. So the problem with requiring training data before the probabilistic retrieval strategy can be used is eradicated with the use of relevance feedback. Okay, so how do we get these initial estimates? The approaches to get these are varied, but some simply sum the inverse document frequency as its initial first estimate. But there are some proposals that do require training data, where we use the curve resulting from the following equation below to find the relevance. So we will get some sample data that we know is relevant or not, and that will make a curve for a term. And then we can use the frequency as a variable so that we can find out if it's relevant or not. Okay, so how do we compute new query weights? We can actually use relevance feedback to compute new query rates for the probabilistic search model, where we use the similarity coefficient of a query and a vector D, which represents the documents in the collection of T terms. I'm going to explain this equation now. DI is assumed to be a binary for if our term occurs inside the document or not, where K is constant. So to get these equation, you do need estimates for PI and UI. And the simplest way to get them is using the following equations. And please notice that there's a 0.5 here. I don't know if I can draw on this. I think I can. In UI, we have plus and PI, we have plus 0.5. This 0.5 is simply an adjustment factor, and it's an estimate. And later we will talk about ways we can actually make this better, because this is a fixed number here that it's not. It may result in some issues later. So when we substitute these probabilities in the equation, we do get one of our conventional weights. Okay, so using relevance feedback, a query is initially submitted, and then some relevant documents may found the answer set. The top documents are examined by the user for relevance, and then using that information from the user, we can compute new weights for the probabilistic model. And then the query is executed again with the new weights. Okay, so there's many variations of composing a new query. Wu and Salton, which are two scientists in the 80s, are very known in the information retrieval research. They tested 4 variations. First is generating the new query using the weights that are computed after only the first retrieval. This is basically the method that we were explaining above. Secondly is generating a new query, but we combine the old weights with the new weights. And they suggested that they can be combined using this equation, where Q is the old query weights and beta is a scaling factor that indicates the importance of the initial weights. And T is the weights computed by using the initial first pass. We can calculate beta by using Ri over R, or relevance times it occurs over the amount of relevant documents, because a query that retrieves that many documents should use the new weights more heavily than a query that only retrieves only a few relevant documents. So basically, the more relevant your term is in the original query, the stronger it should stay in the revised query. Third is query expansion, by combining all the terms in the original query with all the terms found in the relevant documents. The weights for the new query are used as step 1 for all the OR terms, and for terms that occurred in the original query but not in any documents retrieved in the initial phase, their weights are not changed. So we don't punish them for not occurring in any of our documents. This is very different because it allows expansion as well as reweighing. Usually we either reweigh or we expand, but this is mixing them in some way. Before this, probabilistic model retrieval really relied on only the weighing of old terms, but it did not allow for addition of new terms. This is not in the initial query, by the way, because as I said, you cannot add new terms to the initial query for the probabilistic retrieval model, given that it depends on a different retrieval strategy to even get to your weights. So this is talking about adding it in later iterations. Okay, the fourth one is expanding the query by using a combination of the initial weights and the new weights. So we talked about making the new query using the old weights and the new weights. Now we're going to expand the query by using the old weights and the new weights. This is similar to what to the second one, obviously, but with this method we do use different equations, where we are assuming that from the first time it occurs to QM, the weights found in the amount of components in the original query are found after the initial pass. Also, a modified estimate for PI and UI is computed with the following equations. I'm running out of time, so I'm going to try to speed it up. So we talked about the 0.5 in PI and UI earlier, but here, instead of using 0.5, we actually use the key element of the inverse document frequency as the adjustment factor. So they found that this method actually is the most effective, and there's relatively little difference was observed with the modified PI and UI. So overall, different parameters for the variations were tried, such as there are 72 different feedback methods in all. So we were only talking about 4 variations, they tried 72. And overall deck high, which is when we only take the highest non-relevant document, we ignore how many documents we got, found out to be performing the best. Okay. So partial query expansion. Actually, I'm gonna go back to this if I have time, because this is a long explanation. Teacher, do I have time, or?
Today we have just one presentation, so you have time.
Okay, perfect. Okay, partial query expansion. We were talking about adding or reweighing all of the terms in our query. But what if we only selected a few of the terms that are found in the top documents? So that in a paper, the research, the top 10 documents were retrieved, and some of those documents were manually identified as relevant or non-relevant. So this is not automatic. Then we looked at what should be used to expand the original query. Which terms should we use to expand the query? We sorted them based on 6 different sort orders. So what are sort orders, which we will talk about later? They're the ways that we sort the terms of relevant documents. And once the terms were sorted, it chose the top 20 terms. The sort order had a large impact on the effectiveness, and in many of the sort orders, a noise measure, N, is used. This measure for the kth term using the simplest equation is computed as follows. We'll be talking about sort orders in more detail shortly. Okay, so what this equation is where TFK is the number of occurrences of the term in the document. FK is the number of occurrences in the entire collection, and N is the number of terms in this whole collection. So this noise value increases for terms that occur infrequently in many documents, but frequently across the whole collection. So a small value for noise occurs if the term occurs frequently in the collection. It's similar to the inverse document frequency, but the frequency within the individual documents is incorporated as follows. So a modified noise measure is defined as the noise within the relevant set, where pk is the number of documents in the relevant set that does contain the term k. Okay, so what are sort orders? How are we sorting these terms? Well, there's various combinations of relevance number of documents pk, which were used to sort the top documents. The 6 basic sort orders that we tested were as follows. The second from last sort order resulted in the highest improvement to the average position. This is very similar to a sort order which is not written here, which is the basic definition or the basic sort order that we used to use, which is pk multiplied by the inverse document frequency, which is a reasonable measure, given that pk is a good value to use because terms that appear frequently are in relevant documents are usually good to add to the query. But this is not the case for noise terms that occur frequently across the collection. This explains why pk value did not perform as well when it was combined with nk. A follow-up study was done for 6 more different sort orders, and please read the book if you would like to have more information on them. It is very detailed, and I think that's out of the scope of this presentation. Okay, so once the sort order was identified, the number of terms, so we identify which sort order we wanted. The number of terms to add to the new query was studied, and we found that a peak of 20 terms is good. Similar differences were observed in some groups who engaged in massive query expansions, where we just took all the terms in the first phase and added them to the queries, while other groups only used some of these terms. Some groups have even used up to 50 terms and 20 phrases and obtained good results. But it was also found that we can use a sort order which is pk multiplied by NIDF. NIDF is a variable that is the normalized inverse document frequency using pivoted document length normalization. Also, it was shown that using the top 10 items, terms or phrases, results in a 31% improvement in average position over the use of the top 50 phrases. So quality over quantity is good for our sort orders. Okay, so we know how to do relevance feedback, but how many times should we incorporate relevance feedback? Well, we made an experiment where a set of 10 documents was retrieved, a count of the number of relevant documents was made from this set, and then the process continued for 6 iterations. Searching terminates if no relevant documents are found in a given iteration. So each iteration used the basic strategy of retrieval of the top 10 documents, identifying the top 20 terms, and then reweighing the terms, which is the basic relevance feedback that we were talking about. So there are 3 variations that we tested. First, which is cumulative count, which counts different documents and term frequencies within relevant documents and accumulates across the iterations. So this is accumulative. If the term is relevant across different iterations, it will keep accumulating and be more relevant and more relevant. Reset count, it just resets the number of relevant documents and term frequencies within the relevant documents, and I'll reset after each iteration. And third and final one is reset count, which is a single iteration term. Counts are reset and the query is reset, such as that it only contains terms from the current iteration. Okay, so in each case, the number of new relevant documents found increased with each iteration. However, most relevant documents were found in the first 2 iterations. So these are the most relevant. there's a lot of new relevant documents, but there are little relevant. Most of the relevant documents were found in the first two iterations. On average, for iterations from 3 to 6 routinely found less than one new relevant document per query. And all three variations of implementing relevance feedback across iterations performed comparably. So there really wasn't, it really depends on your documents here. So we talked about finding relevance, but how do we found it very tedious to just ask the user to tell us if this document is relevant or not, because they will need to open it and then inspect it and then come out and then say this document is relevant, this document is not relevant. So who should really who will this benefit? When should we let the user decide which is relevant? When should we use automatic? And also, who's going to benefit the most from relevance feedback? In a study done by Spink, it looked at the question of using the talk document suggest terms for query expansion, but giving the user the ability to pick and choose which terms to add. Now, this is different from relevance feedback because usually the user is asked if the document is relevant or not. Here, no. The user was asked to pick which terms to add to the new query for query expansion. So instead of having relevant documents and non-relevant documents and doing all this math and then making a new query, no, the user was just asked to choose which terms to add to the new query. They also studied to determine how much relevance feedback is used to add terms as compared to other sources. So the other sources were query terms. So how do I say this? If you have an original query, and you want to add some terms to it, where are the sources of these terms coming from? There's obviously your original written query. You're going to use the same terms that you used the first time. You can also have an expert or an intermediary telling you what are some good terms for the query. So if you're sick, you're going to search for your symptoms. You're not really going to find anything that's as close as you would find if you had a doctor next to you that told you, hey, you should look for this specific term for your sickness. Intermediate suggestions by the expert during the search. This is basically the same as the second one, but for the second one, they actually identify prior to the search, but the third one, we do it during the search. The source is a book, but now it's more commonly a website where there's synonyms of different words. Maybe you're using a bad word for your search. There's a better word to use here. So the source is alternative source for query terms. And relevance feedback or the selection of terms that could be selected by either the user or the expert intermediary. So the users chose 48 terms, 11% of their search terms, over 40 queries from relevance feedback. Of these, the end user chose 15 and the expert chose 33. This is a very high difference, actually. This indicates that a more advanced user is more likely to take advantage of the opportunity to use relevance feedback. And the user identified which section of the documents found by the relevance feedback. So we have a whole document, which sections of it we actually should be looking for relevance in. Some 85% of relevance feedback terms came from just the title or the descriptive fields in the documents, and only 2 terms came from the abstract of the document. This study concluded that new systems should focus on using only the title and descriptive elements of documents for sources of terms during the relevance feedback stages. This will obviously speed up the process, a lot, because you're not looking at the whole document. You're looking at specifically the title and the descriptor elements. Okay, so in summary, relevance feedback is implementing retrieval strategy in multiple passes, and then refining your query in each pass based on the results of the previous queries. This is by using either user feedback, if your document is relevant or not, or assuming that the top documents are relevant. Something that I forgot to mention is that assuming that the top documents are relevant actually can be problematic if used incorrectly, because you can have something called query drift, where you're heading off in a specific direction, because when you find top documents pertaining to a specific. Let's go back to the John F. Kennedy example. You can somehow find out about his car that he was driving while he was assassinated, and then assuming that that's relevant, you will do a search for the car, and then assuming that that's relevant, you will do a search for the manufacturer of the car, and that's really very far away from what we wanted. Okay, so for the vector space model, we measure how much a word shows up in a relevant document, and then we use that information to revise our query vector. For the probabilistic model, we do our initial pass using a different retrieval strategy. In our example, we use the vector space model, and then using relevance feedback, we can skip over the training data that's needed. We can just compute the weights of the terms. There's many ways of generating these new queries, but overall, deck high, which is where we only take the highest non-relevant document, highest ranking non-relevant documents, performs the best. You can also partially expand the query by using noise measure generated from different sort orders, which results in higher average precision. And the process of relevance feedback could be reiterated, but we found that 3 iterations is the optimal amount. Relevance feedback is best used by an expert user who's knowledgeable about it and about the terms that are coming back from the relevant feedback. And we should really focus on, in relevance feedback, we should focus on the terms that come from the title and the descriptor fields, as they're most likely to be relevant. Okay, are there any questions? I assume there's plenty.
Thank you very much for your presentation. It's a very good presentation. I have just one question.
Yes.
Based on the topics that you covered, what do you suggest to general users who run queries over Google, or, for example, as a student, you may need to find some papers from Google Scholar. So how would you apply these techniques to improve your search?
Well, when you are searching, we really want to use terms that are going to be important in your specific paper. So maybe there's a term that's generally available in a lot of papers, but it is in your paper also, but maybe omitting that out of your search and then just keeping what's specific for your search is good. So in other words, quality of your search is better than quantity of your search. So having a few terms that are relevant to what you're searching for is better than having a lot of terms that some of them may be non-relevant. So I would say focus on quality over quantity when you're searching for such thing.
Yes, but first you write some keywords and
Yes.
begin searching, and the system returns you some results, and you check the titles, and you
Yes.
may identify that you need to insert some related terms from the titles of the relevant papers, and you rerun your query, and you may see that some words are not related with your query, so you remove these terms, and you repeat this 2 or 3 iterations, then I think you will find the most relevant papers with your topic. Okay.
This is the human version of relevance feedback.
Yes, of course. Thank you very much.
Thank you.
Is there any other question from the class? No question?
Don't be shy, guys.
Okay, thank you very much. I'm stopping recording now.